Hello everyone, my name is Rakita and welcome to my channel. Due to the prevailing situation of the country, a lot of things have come to a stop, which includes your education as well. So I thought of doing some online lessons for students who are planning to sit for their G.C.E. Advanced examinations this year. I'll be covering a few chemistry lessons. I'll be starting off with a physical chemistry lesson, equilibrium. I'll be putting out a series of videos that will cover a series of other lessons. I hope you find these videos useful, and if you have any suggestions for future videos, please do let me know. Let's get on with the lesson.
Alright, let's start with the lesson, which is equilibrium. So before we get on with the lesson, let's make sure that you understand the certain things very clearly. So there are two main types of reactions that you have to be aware of before starting on with the lesson, which is irreversible reactions and reversible reactions. Irreversible reactions suggest that these reactions, once they happen, they cannot have the backward reactions happen again, right? So in other words, the definition that they have been given is reactions which go to completion and never proceed in the reverse direction are called irreversible reactions. So they only go towards one direction. So these are all also referred to as unidirectional reactions. For instance, if you burn a piece of paper, it will completely burn out, and at the same time you will have smoke and ash as products. So you can't take smoke and ash and put them together to form a paper again, right? So that is an irreversible reaction. That means it cannot go backwards. So reversible reactions, on the other hand, are quite different. These reactions are also referred to as equilibrium reactions. Reactions which never proceed to completion in both forward and backward directions are called equilibrium reactions or reversible reactions. So I have a small example given here, which is A and B reactants going to becoming products which are C and D. So you might see this reversible reaction equation arrow here. So in this case, this means A and B has the ability to become C and D, and at the same time, the products which are C and D can react with each other and produce the reactants which are A and B. This kind of reaction will never go to completion. They will always, at one point, have the same speed of converting from A and B to C and D, and same speed will be there when it comes to converting C and D to A and B. So when the rates at which each of these reactants and products convert into each other become equal, we say an equilibrium state has been achieved. So to put it in simple terms, let's take a look at this one. So let's say in tank A is products, tank B is so tank A is reactants and tank B is products. So pump F would represent the forward reaction, pump B would represent the backward reaction. Let's say these pumps are capable of pumping water at the same speed. Let's say 1 liter per second, both of them. So just to make things interesting, I made sure these two tanks have two different water levels, right? So keep that in mind, and let's think about this situation. If you turn these two pumps on at the same time, you will realize since pump F and pump B, since they have the same speed and since they are pumping water into two different directions, what happens is water levels of each of the tanks will remain stable. So if you open the lids of each of these tanks, you will see the water level don't go down. It will stay the same. Why is that? Because when water pump F is taking, let's say, 1 liter per second from tank A to tank B, same amount of water, which is 1 liter per second, is taken from tank B to tank A, right? So at any given moment, the amount of water that is being transferred back and forth will be the same. So if you just open the lids after these pumps are turned on, if you just open the lids of each of these tanks and just observe from the top, you will see, although the pumps are working very hard to pump water back and forth, the water level will not go down. So when you observe from outside, it looks as if there's no pumps turned on, right? But in reality, there's an equilibrium which is referred to as a dynamic equilibrium. That means it's not the fact that these pumps are closed and water is not going anywhere. It's the fact that water is going back and forth. So it's a dynamic thing, and at the same time, it stays. The water level stays the same. So it's an equilibrium. It's a balance, right? So this example will kind of make you understand, if the backward and the forward reactions are equal, or the rates of forward and backward reactions stay the same, reactants concentration and the product's concentration will not change, right? So A and B, as much as A and B kind of get consumed to produce C and D will produce A and B back, right? So that means it keeps going back and forth, and the rates are the same. The concentrations of both reactants and products they stay the same, and that is referred to as equilibrium state. So let's take a look at the definition of chemical equilibrium. Chemical equilibrium is a state in which both reactants and products are present in concentrations which have no further tendency to change with time, right? So then they go on to say, so that there is no observable change in macroscopic properties of the system. Let's go back to this slide again, right? That means when the forward pump and the backward pump keeps pumping water at the same speed, the amount of water present in tank A stays a constant volume, and amount of water present in tank B also stays as a constant volume. So the water levels of each of these tanks will not change, right? Does this mean each tank has to have equal amounts of water? No, not necessarily. That's why I kind of intentionally changed the water levels, right? Since 1 liter of water is taken from, let's say, every second, 1 liter of water is taken from tank A to tank B, right? To simplify this further, let's say tank A has 20 liters and tank A has 50 liters. So when 1 liter of water is taken away from tank A, the remainder is 19 liters. But as soon as 1 liter is taken away from tank A, another liter is put back in the tank A through pump B. So the amount of water that stays in tank A will be always 20 liters. Let's take a look at tank B. The same thing. When pump F brings in 1 liter, pump B takes off another liter. So it never goes over 50 liters, right? So you can have two different values, and if the rates of the reactions or rate of the pumps remains the same, the water levels will remain the same. So they say there should be no observable macroscopic properties such as color, smell, or any concentration changes will not be observable, right? So even in this case, the water level will become a macroscopic property which will not change. So it seems as if there's a static equilibrium, but in reality it is a dynamic equilibrium. Dynamic means there's something always in motion that you don't normally, now in this case, which you don't normally see. Reaction rates of the forward reaction and the backward reaction become equal. That's what we were talking about all this time. And you have to understand that this is not static balance. This is a dynamic balance. That means, now let's say if you just fill the two tanks to, like you just don't have any pumps, just picture this without any pumps or any tubes connecting the two. Tank A is on its own and tank beats on its own, and they just maintain their water levels without any pumps involved in it. So if that happens, it's just a static balance. That means there's nothing going on. They're just on their own, containing the amount of water that they have. But dynamic balance means water keeps moving from one to the other, whilst keeping the volume of each of these amount of water in each of these tanks a constant. So that becomes a dynamic equilibrium or dynamic balance. Right? So irreversible reactions versus equilibrium reactions. This is something you have to understand now. Reading of graphs are also quite important when it comes to chemistry. Now you see in the left hand side graph, which is the irreversible reactions graph that we have plotted against concentration versus time, you can see we normally put in the reactants first, A and B, right? Reactants get used up to produce products. So at one point in a unidirectional reaction or irreversible reaction, all of the reactants should get completely consumed to produce products. That's what is present in the first graph that is here. You can see A and B has a high concentration initially, and as time passes by, you can see the concentration of A and B kind of keeps decreasing. Whilst that is happening, the concentration of products keep increasing. Why? That means concentration of A and B decreases means they get used up to produce products. So product concentration gradually increase. So at one particular point, all of the reactants will be used up, and it will completely be converted into products. So at that particular point, the reaction will completely stop. There's no equilibrium or anything, just completely stop, and then there's going to be only C and D, right? So this is referred to as completion. Reaction is completed. All of the reactions that we put in are completely used up. That is an irreversible reaction. But the scenario with equilibrium reactions are quite different to that. Now you can see, again in this case, the reaction is A and B going to C and D, but in this case, we are making it an equilibrium or reversible reaction. That means there's tendency of both the forward and backward directional reactions happening. So initially starting, we only put A and B. So the concentration of A and B is going to be high. So like in the previous case, when the reaction proceeds, the concentration of A and B decreases. Why? Because A and B keeps getting used up. So as and when A and B gets used up, the products, which is C and D, keeps getting formed. So the concentration of C and D keeps increasing. As you can see from the blue line kind of keeps gradually going up the curve, whereas A and B gradually keeps coming down. But unlike in the previous graph, A and B does not completely get used up. At one particular point, A and B concentration plateaus and kind of stops from going down any further. Same happens to C and D concentrations. Now you might think, did the reaction stop? Did it come to a stop? Not necessarily. At this particular point, we say an equilibrium is achieved. You may ask why that is or how that is happening. This is mainly happening because at this particular point, A and B, or the reaction going from reactants to products and reaction going from products to reactants have the same rate. In other words, or simplified words, forward reaction and backward reaction rates become equal, right? So this particular diagram will explain it further. You can see initially when you're starting the reaction, you have more of A and B. That means we only put A and B into the system. So in that case, really high concentration of A and B is there and no concentration of C and D is present. So when there's high concentration of the reactants, obviously rate should be high. You can see we are starting off of a higher rate. But as and when the reaction proceeds, A and B concentrations keep going down. So concentration is normally proportional to the rate that is there. So as the concentration goes down, rate goes down. But this is not the case with the products that are being formed. As the forward reaction proceeds, more and more products will be formed. So when more and more products are formed, what happens is the concentration of products increase. Concentration of products increase means rate of the backward reaction, which is starting from products, increase. Right? Rate of backward reaction keeps being on the rise. So rate of the forward reaction keeps coming down, rate of the backward reaction keeps coming up. At one point, these two reaction rates become equal. That particular point is referred to as the equilibrium point or equilibrium state, and you can clearly see that in this graph, right? So again, at equilibrium state, reaction is still happening. A and B are in fact really reacting with each other and forming C and D. And whilst that is happening, the same rate that reaction happens, C and D are reacting together and forming A and B. If you understand this bit properly, you understand equilibrium to a great distance, right? To a great extent, sorry. So, moving forward from there, when we are learning about equilibrium, there's another thing that we have to learn: the systems, different types of systems. Equilibrium can, before I get into that, let's learn about the three different types of systems: open system, closed system, and isolated system. Now on the right hand corner, depicted from diagram C, you can see that it's an open beaker which normally kind of allows energy to come out and energy to be released, and at the same time not only energy but matter to come out and matter to come in and matter to go out, right? So it allows both energy and the matter to be exchanged, right? That's what I try to show, like a ball kind of falling into the beaker and water splashing out, right? It allows material to come in and go out, and at the same time energy to come in and go out. Then we talk about closed systems. Closed systems do not allow any matter to go out or to come in, but it does allow energy to be exchanged, right? When it comes to isolated systems do not let neither energy nor matter to be exchanged, right? So you can see it is completely covered by completely covered by something that doesn't let energy to come in or go out. So after analyzing these three systems, you have to understand equilibrium can only be attained in closed systems. That is mainly because of this particular reason. Imagine this, right? You do a reaction where the reaction produces a gas, and the gas is the product. So if it's a reversible reaction, gas has to be in the system for it to react with each other gas molecules or each other products or each different products that they produce, and react with each of them and form reactants again, right? Let's say A and B are liquids and they form C and D as gases, right? So let's say C and D has to react to form A and B again. So if the system is open, as soon as C and D are produced, those two gases will exit out into the atmosphere. So when that happens, it's not in the beaker anymore, it's out in the atmosphere, not in close proximity for them to react and produce reactants again. So due to this reason, equilibrium reactions or equilibrium cannot be attained in an open system. It has to be done in a closed system. So just to round it all up, there are a few things that you should remember or gather from this particular class. At equilibrium, product and reactant concentrations remain the same. That means when the equilibrium state is obtained, neither the concentration of the products nor the concentration of reactants will change. Right? They are remaining a constant value. Starting point. So, since we are talking about a reversible reaction, it doesn't matter from which end we start the reaction. You can have A and B put into a container and then an equilibrium obtained. Now, we were talking about A and B going into C and D. You can either have just C and D put into a container and going into A and B, right? And obtaining an equilibrium there. So, it doesn't matter from which end you start the reaction. You can still obtain equilibrium reaction if it is a reversible reaction we are talking about. Need a closed system. I just told you earlier, only in a closed container a reaction can be considered to attain equilibrium, since no part of the reactants or products can escape out. Alright guys, so that is it for this lecture. So I will continue on to explain to you and give you some examples about proper chemical equilibrium reactions. I will talk about microscopic properties, physical equilibriums, and chemical equilibriums separately. And at the same time, I want you to kind of suggest what you want me to cover in the future so that I can prepare now itself and then cater to your needs. Right, stay safe and keep learning. Thank you.